Back. Today we're going to talk about a few basic periodic trends. Normally this is going to be a unit in the first maybe 3 or 4 chapters of the chemistry textbook. When you get to the periodic table and before bonding it'll talk about some periodic trends. Let's go ahead and look at a few trends. First of all, we might have to mention valence electrons, but this isn't really a video about valence electrons. That's an entire video by itself. We're going to look at ionization energy, shielding, atomic radius, ionic radius, and electronegativity. So let's jump right in here. Ionization energy. The definition says the energy required to remove an electron from a gaseous atom or ion. Well, what does that mean? Let's go ahead and look at this chart here. What that means is for some of these elements, it's going to take more energy to get an electron off of it, to pull an electron away from it. Let's go ahead and look at the trend here. Here we have lithium. It takes 520 kilojoules. Kilojoules is an SI unit of energy. Fluorine takes 1,681. So it takes a lot. And then, of course, these noble gases. Look how much energy it takes to get an electron away from the noble gases. Well, part of the reason for the noble gases is that they have full electron shells. This is something you should have learned in the valence electrons video. They have full shells, and that makes them extremely stable. And they do not want to give up electrons. It's going to take a lot of energy to get an electron away from helium. And fluorine also doesn't really want to give up any electrons. But why is that? Why does ionization energy increase going across a period? That's what these are, periods, and these are groups. The columns are groups. And it seems to decrease going down a group. Well, let's go ahead and look at the periodic table and see if we can figure it out. Let's go ahead and look at period 2. We have lithium all the way to fluorine here. Well, part of this has to do with a nuclear charge. Remember, lithium, if we look at this, has 3 protons in its nucleus. So we can say the nuclear charge of lithium is +3. And it has the first energy level. This is all back in electron configurations. Has 2 electrons. That third electron is in a second energy level, sitting right here. So you could say that the +3 charge of the nucleus is going to pull on these electrons. It's going to keep them bound to the nucleus. But if I get over to, say, nitrogen, there's 7. I have to draw 7. 1, 2, 3, 4, 5, 6, 7 protons. Here's the thing. It still only has 2 energy levels. Remember, everything across this period is in the second energy level. It just has more electrons in them. Here we have hydrogen and helium. That's just in the first energy level, which can only hold 2 electrons. So as we go down, we add energy levels. But across the period, we don't. We add protons and neutrons, but we're in the same energy level. So here we're going to have 2 electrons in the first energy level, and then 1, 2, 3, 4, 5 in the second energy level. Well, the nuclear charge on this is +7. Notice how all these protons are together. Together, they are stronger, and they will pull on these electrons more. And since this nuclear charge is greater over here, it does not want to give up the electron. That's why as we go across a period, the ionization energy increases. And that's actually why the noble gases are noble to begin with, because if I go over to neon, I have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Let's say this is neon, and then I would have to add 3 more protons. Neon would have a plus 10 charge in the middle, and now it has full energy levels. The first and second energy level are full, so this is the perfect situation where neon's going to really grab on to these electrons and not want to let them go. So by understanding ionization energy and energy levels, we actually understand why something is a noble gas. It's kind of one of those things in chemistry where they just throw this down and say these are noble gases and they tend not to react. And sometimes you really don't know why. It's just something you have to memorize. Well, this is why right here. So if we go back to our little diagram, we can see that this table shows us that trend. Now, as we go down, we're adding more energy levels. So as I go to sodium then potassium, it has a lower ionization energy. And that's because, think about this, lithium, there's plus 3, has first and second energy level, 2. But as we go down, we're adding sodium, we're adding a whole nother energy level. And then I keep going down, adding more energy levels. So it gets harder and harder for that plus charge down here. Even if there are more protons, it's going to get more difficult for it to grab electrons that are farther away. The basically atomic radius is increasing. The distance from here out to the outer edge of that electron cloud is increasing. So that's why the ionization energy down here is actually lower. It's going to be easier to get electrons from these elements. But across the period, it still increases. And I think if we go over to this diagram, it helps us understand this a little bit. Energy levels. We've been talking about lithium. There's 2 energy levels. And as we go across the period, there's still 2 energy levels, just a lot more electrons. And there's more protons in the middle, which this doesn't show. But as we go down a period, we're basically adding more layers to the onion. Now, of course, the orbitals don't look like this. We know that they have different shapes, but it helps us visualize what we're talking about. So this distance is greater right here. And let's talk about the consequence of that. One consequence is that these are non-reactive because they have full valence shells. But another consequence is these halogens are very reactive. Fluorine is extremely reactive. It wants one more electron. This is because of the valence shells. And it's not going to give up electrons because it has a high ionization energy. Now you've probably noticed something that may or may not be confusing. You notice how as we go across, it doesn't actually steadily go up in a nice little curve. It goes up and then it kind of goes back down, then up, then back down. You're probably thinking, why? Why does that happen? Well, I don't want to get into too much detail here, but basically as you go across, let's look at this chart here. This is the first period, but here's the second period. As you go across the period, here's neon, so that would be on the right, and here's lithium on the left. Depending on how the electrons are actually in the orbitals and the shells actually makes a difference. Remember, what we're really talking about here is a bunch of charges interacting together. All of those electrons are negative and they're basically repelling each other, and the way that they're in the shells affects ionization energy. So for instance, if we get up here to nitrogen, nitrogen actually has the situation, now if you remember, the p subshell has a total of 6 electrons. And as you can see here, it's half full. As it turns out, when the p subshell is half full, there's 1 electron in each orbital there. It actually makes it much more stable. But once you add 1 more electron, that 1 more electron has to interact with one of these 3 electrons, and they repel each other, and it makes it easier to basically grab that electron away. So it does go up from left to right, but it doesn't go up in a nice curve like this or a nice straight line. Let's go down to the second topic, shielding. We've already actually just kind of touched on shielding, because when you talk about these things, you're talking about all of these things working together. But shielding is this idea. Here's the nucleus. Now notice it just says Z. We don't know how many protons are in here, but we notice we have something, and we don't even know what, this definitely isn't the first shell, because the first shell would have more than 2 electrons. Let's just say there's some shells, could be the third or fourth shells, out from the nucleus. Well, the way that these electrons interact with each other actually matters. Remember, these are both negative charges. So if these are closer to each other, they repel each other more. Here it says repulsion. They're pushing away from each other. So the nucleus is trying to grab each one of these. It's trying to say, hey, come here, come here. But at the same time, these are repelling away from each other. And sometimes when these are close enough, they might repel also. And also they will shield electrons. So think of it like this. These inner electrons, these are in an inner energy shell, pretty much are a wall. They make it so the nucleus has less pull on the outer electrons. It's sort of like if you're standing back from, say, a concert and you're not right near the stage, you may hear less noise, or you don't really get the full effect of the show because you're out here on the edge, or you're standing farther away from the sun and people are in front of you. They're kind of like shading you from the sun. So these outer electrons don't get the full pull, and as a consequence, as you start adding more and more shells, it gets easier to pull one of those electrons away, because they're not going to feel all of the nuclear charge. Shielding and repulsion, basically, I already mentioned in ionization energy. Let's go ahead and look at atomic radius. Well, atomic radius is simply the distance from the center of the nucleus to the edge of the electron cloud. So it's like a radius. We already know what radius means. But here's the weird trend that really confuses people. Definitely confused me for a while, and you have to sit down and think about it. As we go across a period, the atomic radius decreases. Here's neon. Here's lithium. You're probably thinking, how? Why? What the? You know, lithium only has 3 electrons, right? I'm just going to put 3 electrons here. And this has 10, and this has 3 protons, and this has 10. How in the heck shouldn't this be bigger? There's more stuff there. There's more electrons, there's more neutrons, there's more protons. Why isn't it bigger? This should be bigger. And that seems very logical. You think it should be bigger. But yet again, remember what I was just telling you about nuclear charge. The 10 protons, I'm not going to draw all of them, let's just say plus 10. The 10 protons in this nucleus are grabbing all of these electrons. And remember, there's still only 2 energy levels here. This has 2 energy levels, this has 2 energy levels. That's what we have to remember. This has 3 energy levels, this has 4. So as we go down the energy levels, there's more skins to the onion per se. But over here, there's still only 2 energy levels. So we can really grab those electrons and pull them tightly. They actually are closer to the nucleus because it's pulling them towards the nucleus. But down here in sodium, let's say this is the nucleus of sodium, it's going to have a first energy level, a second, and then a third. And so because of shielding, remember how we just talked about shielding? These electrons here shield these outer electrons from the full nuclear charge. So it can't really pull as tightly on these, so these are floating farther away from the nucleus. They're out here farther. So yet again, as a good illustration, if we look at this, as we go across a period, we still only have 2 energy levels here. We have more protons and we have more electrons. But those protons are what matters because all those protons are together. They're right next to each other in the nucleus. So all those protons are working on each individual electron. It's also kind of hard to understand. Remember, it's kind of like the sun. The sun has a gravitational pull. It's pulling on the Earth. But if we add some more Earths and some more planets in our solar system, the sun is still going to have the same amount of pull on the Earth. You know, if we add couple more suns right next to each other is going to have an even greater pull on each planet. So if you think about it like that, atomic radius makes sense. Okay, well, that's atomic radius. What the heck is ionic radius? Ionic radius is the exact same thing, except it's when something forms an ion. So, for instance, if I have lithium, which say it loses an electron, so lithium will actually be plus. Lithium cation. What about the ionic radius? So what about the distance from the nucleus to the outer edge? And obviously it's going to decrease. So if I take an ion, well, here's the thing. If I take a metal cation, it will decrease. But if I take an anion, it's going to increase because I'm adding electrons to it. So we have to go ahead and look at the periodic table to figure that out a little bit. And this is all about ions. We're going to get cations over here and anions over here. All that means is the metals over here are much more likely to lose an electron. And that is actually because of the ionization energy. It's going to be easy to take an electron here, not so easy to take an electron here. In fact, this will lose an electron, this will gain an electron. So that's why these will be cations over here, meaning they will be positively charged atoms, and these will be anions over here. They'll be negatively charged. So actually, the ionic radius for metals will be smaller than the atomic radius, but for anions it will be greater. That leads us to the last thing we're going to talk about, which is electronegativity. Let's go ahead and look at the definition. Electronegativity is a measure of how strongly atoms attract bonding electrons. So that's kind of similar to ionization energy, but this is just taking something away, whereas this is attracting something. And actually there's a scale that goes up to 4, and this is based on actual studies in a lab. So if we see here, fluorine has the highest electronegativity. Or if we go down here, we have a 0.7, which is basically the lowest. So the scale, more or less, is supposed to go from 0 to 4, but basically 0.7 to 4. Notice how these have no electronegativity charges or scales on them. That's because these are noble gases, and noble gases are not going to attract electrons because they have full valence shells. Well, this all ties into ionization energy and also how many electrons are in the outer energy levels. Remember, fluorine only needs one electron to be like neon. So its ionization energy is actually high, so it's not going to lose electrons. And that means it's going to very easily find one electron and bond it to itself so it can become stable. And that goes with all these halogens. See how these halogens are extremely electronegative? They have high electronegative charges, whereas these alkali metals have very low charges. So these are not going to take electrons. They're not going to gain electrons. And that means that these metals are likely to bond with these nonmetals over here to make something called ionic compounds. So they will form ionic bonds. We haven't gotten to bonding, but there's 3 or 4 different types of bonding. And based on these charges, we know a lot about bonding. So if we know, based on the difference in electronegativity, we can look at what type of bond is likely to form. If there is a 2.01 or higher around about, it's going to be an ionic bond. Well, lithium and fluorine, that's 3 right there. The difference is 3. So if I look down here, that's got to be an ionic bond. I already know it's going to be ionic. If I go back, sodium potassium, these are all going to bond over here and be ionic bonds because there's going to be a high difference. If that difference is lower, see down here, it's going to be covalent, which happens a lot in the nonmetals and some of these gases over here. So, say, if I take carbon dioxide, it will be covalent. Carbon will bond with two oxygens and it will be a covalent bond. Or I could have something that would be slightly polar or very polar. So as I go down, as that difference in electronegativity gets higher, the type of bond is slightly different, and it tells us what type of bond it is. And that's important to know before we get to that unit on bonding. We'll keep going back over this and referring to this. But then we suddenly realize why there are different types of bonds. Well, that was just a very brief introduction to periodic trends. We could spend more time on it. We could look at valence electrons a little bit more and some other things, but I think that's going to be sufficient for a high school chemistry class and what you need to know on a test or a quiz. So thank you for tuning in, and I hope that helped you a little bit.